Software development for real-time embedded systems. Project 2.
First things first, let's go over our build. Our team decided to use two temperature sensors in order to compare them. The first sensor is the DHT11 temperature and humidity sensor hooked up to the power, ground, and to digital port 8 on our Uno. The DHT11 sensor is actually a microcontroller combined with a thermistor and humidity sensor. Because of this, we can interface with the controller digitally instead of analog. The second sensor is a thermistor I got from my Uno starter kit. It came with example code including the algorithm required to convert the thermistor's analog output into Kelvin, then to Celsius, then finally to Fahrenheit. The thermistor has a 10k ohm pull-up resistor and is connected to analog 0 on the Uno.
The code implementation for the project is a simple round robin with interrupt design in Arduino Sketch. We have the included DHT11 library, a definition for periodicity of each respective sensor, 10 seconds per read, offset by 5. This was to emulate separate interrupt times, but they could be performed together without issue. Timer 1 is configured at startup for a 1 Hz interrupt, pairing a 1K prescaler with a 15K register compare value, which divides the 16 MHz clock down to 1 Hz. The code to establish a timer 2 interrupt is included but commented out. We did successfully test the two sensors using distinct Arduino timers to trigger interrupts, but for simplicity, the demonstration only uses timer 1. For timing, we grab a baseline startup time using millis, which reports the number of milliseconds since boot. Then we enable interrupts so we can get this party started. In our ISR for timer 1, we have almost minimal code, incrementing a global second counter from 0 to 9 with rollover. At the specified singles digits, the respective sensor service flags go high. If we broke out into separate timers, we could do this much easier, not having to go through these extra conditionals. We've created a common time printing function to report the number of milliseconds since boot, subtract the baseline from earlier, and then print this to serial in a seconds.milliseconds format. Since there's no real-time clock available in this design, we report the number of seconds since startup. And our main loop is a simple round robin, polling against the sensor service flags only. If either is driven high by an interrupt, we enter the if statement. For DHT, this involves a while loop of about a quarter of a second to comply with the DHT11 library, iterating through an internal state machine with 250 millisecond cooldowns. This returns with a Celsius float, which is converted to Fahrenheit before being printed out with a DHT identifier string. And for the thermistor, we read directly from the analog input pin and conduct a known set of math to eventually convert our way to Fahrenheit. And of course, in each instance, we lower the service flag from the interrupts so that it can be triggered again in 10 seconds time, and we print the time since startup.
Here we are, stage for execution. Got my Arduino, my DHT11 sensor, and my thermistor all right here together. There you go, you can see the thermistor a little bit better here. I'm going to give the sensors a few reads to get stabilized after being powered on before starting the experiment. As you can see in the PuTTY terminal, we are getting a temperature reading every 5 seconds, with the period on each sensor being 10 seconds long. Alright, now we're ready to go ahead and start the experiment. So let me just put the system in the fridge. Alright, there we go. And we will be back in 5 minutes to pull it out. Alright, 5 minutes have gone by, so let's get the system out of there. And there we go. Now it's time to let it sit for another 5 minutes at room temperature.
And while that demo occurred, we printed our results out to a CSV file. We put it in Excel and did some funky graph manipulation, which eventually leads us to our results right here. There's an interesting distinction in how these two sensors react to the changing temperatures. The thermistor is much more immediately reflective of the drops and subsequent raises when we take it out of the fridge, while the DHT maintains its temperature for longer periods of time, showing a slow drop inside of the fridge and a somewhat faster return to form, though not as dramatic as the thermistor by itself. And that concludes our demonstration for Project 2. Thank you for watching.